So in this Zoom session, we will discuss two topics, or more than discuss, we revise and then try to clarify if you have any questions. The first topic is on increasing the sampling rate by an integer factor. The second topic would be on changing the sampling rate by a non-integer factor, a number that can be expressed as a rational number. Okay, that's the agenda for today's Zoom session. So let me now switch off my video and go to notebook mode. Okay. Yeah, stop the video and then share the desktop, share screen. Okay. Hope my screen is shared now. Let me move on to OneNote. Okay, we are here. So let's first go to the sixth module of the sampling, which is on increasing the sampling rate by a discrete time signal, right? So what is the similarities or differences that you think of for increasing the sampling rate of a discrete time signal versus given xs of t, right, in your reconstruction of the signal, and from that constructing xr of t? What are the similarities and what are the differences? What do you think? So is the question clear? So the second module in sampling was, or the third module was to reconstruct the signal from discrete time signal. You would like to reconstruct the continuous time signal, right? So we were doing it from x of n. You get from there. Let me also maybe just scribble here so that things what I'm talking would also make sense. So assume that, so what you are doing while in the reconstruction of, okay, reconstruction of continuous time signals, what you are doing there, if you recollect the third module in the sampling, you had x of n. From that, you give it to the digital to analog converter. You get, let's say, xs of t, if you recollect, right? So from that, you give it to some h of j omega, is it not, or hr you call it, and from there you get xr of it. That's one thing. Okay, now the another thing in the module that we are now going to discuss is you had a signal, you want to upsample it. So in a way you have an expander here, right, followed by some hr of n here, reconstruction, and are increasing. So you call it with whatever name it is, hr of n, or let me call it maybe hi of n, as I am increasing the sampling rate here, and let's assume that xi of n here. Okay, do you see any similarities that were happening here, and the differences then followed by that? What is the yeah, maybe first let's take a look at similarities. What is similar in both cases? What's the first dominant so the most critical common thing, what would you say here? Hello, no one? Yeah, try something. No, no attempts there. Am I audible in the first place?
Yes, sir.
Okay, yeah, make an attempt. That's absolutely fine, even if it's not correct. I just would like to see some guesswork here. What is it what's the kind of operation that is common here, or what's the kind that would be you would be doing here? In what way are they similar conceptually? If not exactly, just tell me what is it that is common here in conceptually. Or do you want me to keep it more, bit more specific? Say I have a signal here, x of n, okay? xi of n is, what am I doing here? When it comes, suppose my L equal to 2 here, then what I am doing, I am introducing here in between, the expander introduces in between zeros. And what would be the next step of hi of t does? After that, what's the job of hi of n here? This module. That's the expander, what it does, right? The signal is, for example, xe of n here. Is it not? So then what does this hi of n will do here?
Interpolate.
Sorry?
So it will interpolate.
That's all, right? You now interpolate the values in between, okay? Based on the values that are there here. Is it not? So how do you interpolate it? Using a sync function, right? So how the sync function is there, for example, assume a bigger signal there, where I am keeping, let's say, upsampling by a factor. What's the upsampling factor here for whatever I am drawing? Okay, assume that, okay, I am drawing it for some, let's say, some other signal here, okay, because I don't want to erase it. Okay, what is the L value here?
4.
Yeah, that's right. So then what would you do? You are going to interpolate, okay, the values at these newly introduced points. Okay, now you, here, for example, this is your 0 1 2 0 1 2 3 4 5 6 7 8 and so on. So what would you do now? There is a sync. You could think of a, okay, sync here, and another sync function here. Okay, well, this is not an accurate drawing here. What's the wrong with this? Is this the way? Yeah, by the way, before I erase it, do you see any problem with the way I have drawn it?
The sync is discrete in this case.
Right, that's what the first thing, correct. What's the, so assume that now instead of that I have drawn in the envelope of it. Okay, that's spot on, that's correct. What is the other mistake I made here? There is yet another mistake I made here.
Sync should be 0 at those integral points. But
yeah, those were integral points, right? 1 2 3.
Yeah, at 0 it's not. I mean,
okay, that, yeah, assume that I drawn, yeah, I understand. This should have, okay, oops, it should, can I go back? No. Okay, assume that still I have drawn it properly at 0. That also assume it, but still there is some other mistake is there in whatever way I have drawn it. Anyone able to trace that mistake? Take a look at the formula and tell me now. This is the way you do it, right? Now you tell me where is the mistake. So this is how I have drawn it. Okay, let me again since that got erased. Okay, I started with a wrong way of drawing it, of course, again dotted, but still there is one more mistake in the way I have drawn it.
It should not be 0 at all other points. Like,
very good, that's correct. It should be 0. For example, the one which is there at 4 should be 0 at 0 only. Very good, but not at these points, because look at the sync function. This is sync of pi by L into n minus KL, right? So for varying k, it would be, unlike the reconstruction of in the first case of reconstruction, unlike the case here, it's a different case here. So essentially, okay, this function would be something like, oh, oops, I should not have done that, but again, it's okay. So assume that I have a value here that would come something like this. Okay, not in between there. See the way the function, again, I should be drawing a dotted line there. The same thing happens here also. Okay, again I'm drawing it very badly, the sinc function, but that's the mistake I made there. Okay, so by the way, you now draw the sinc functions. Yeah, this is slightly difficult, but yeah, that should reduce, the value should reduce. Okay, similar to what you had seen earlier in the decreasing sampling rate. But now what should happen now is all the things combined would give you the summation of all those things, would give you the value here. So essentially you are interpolating here. Okay, so in both cases, what is common, what I would say the strong point is interpolation of the values that have been at those points that have been newly introduced based on the values that you have already having here. Okay, so 0 1 2 would now go to the upsample by 4, so it will go to 0. L is 4, so 1 times 4 is 4, then 2 times 4 is 8, and in between, and this of course up to minus infinity to plus infinity of this k values, you would be drawing them up and summing up would give you the signal here. If you look at the final expression, that's essentially what is done here. Okay, the sinc function at each point again weighted by that sinc function where it has been kept at that point, what's the value is scaled by that. Whereas here, well, that's the difference there. There is no zeros here as such. In your case, what was the other case there? You had a continuous time function. This is what I would say as the key difference, okay, in my opinion. So this was already your x s of t. Okay, both are continuous time here. Whereas here, this case, this is a discrete time signal. You are getting out of it a discrete time signal. Here you have a continuous time signal. You have a continuous time signal here. Here also you do an interpolation, right? And this would be something. Okay, yeah, again that sinc value should keep dropping, but you could notice here this value would be 0 at all the integer non-integer values, but again this is not the case here. This is say sine of n minus kl, okay, by the equivalent sinc function in the discrete time domain you have. So here you would use, so that's the difference. So you had sinc at every n value. Here of course n means here n times capital T, okay, because that's a continuous time function. Whereas here the sinc functions you would keep only at those values where you already know the value, and then it is in between you need to interpolate. Okay, and one more difference you could see here is this gets expanded when it comes to from here to here. You could see interpolating is because the time axis, this has nothing to do. So this is n, you have that information of t is missing there. So because of that, this gets, the axis gets expanded here. Whereas here the axis would remain same, but in between these nt values, okay, xc of t equal to x of nt, xc of nt would give you x of n value, right? No, from x of n, you in fact got xc of nt, it's the other way around you got it. So only at those points nt you have it. So in between intermediate t values, which are not integer multiples of capital T, you are interpolating it. Is that clear? And let's quickly take a look at the way we were doing here. You are increasing the sampling rate. You could see here the t-axis, whichever, the moment you are going to the expander, your in a way your n is getting scaled up. So in the frequency domain, things would come close, right? The moment you are applying the expander. So that's what, suppose this is the, for x of n, this is your dt, if this is the dtft of your x of n, the moment you are from there to going to x of e power j omega, if you are upsampling by 2, then what would happen? This t has now as in fact become t by 2 here, correct? So so if you look at x of n, whichever is there at, for example, at 1, it will go to now the L times n, so that is expanded there. So that would contract things. So from pi, this would come to pi by 2, because omega times t1 is t by 2. So that axis would get scaled up by 2. Suppose if it is 4, if you are upsampling, expanding it by 4, you would get here pi by 4 and so on. That's the first step you are doing. The next step you could see there is you are going to interpolate them with a sinc function. That sinc function is having a periodicity again, so minus pi by L to plus pi by L, because see, yeah, well, I have this omega anyway, cutoff frequency, if you take it omega cutoff, the similar one cutoff is omega in case of capital omega scale, this you take it at omega s by 2. In terms of the cutoff here, that turns out to be 2 pi by t into t by 2. So yeah, essentially that would give you pi by L would be the one copy you are getting here. See, again, think of it in this way. When you are upsampling, so what was happening in while you are when you are converting a discrete continuous time signal to discrete time signal, depending on your t value, right? You are getting as many copies of it placed at nt each one. But the moment you are increasing the upsampling is decreasing the nt. So you have, so what you should do here is upsampling is increasing or decreasing t. Upsampling is decreasing the t value, right? You are taking more samples of it. That means more copies would be coming there, right? So that's so essentially now from so that's why what you need to do is you have more copies there, right? Well, or maybe the easier way to look at it is just look at it this way. You already seen that this is a low, you have a interpolation there that would be essentially equivalent to doing a low pass filtering. Or another way of looking at it is we have seen it graphically from there. Okay, so where we have seen it is at t, if it is going to pi, at t by 2 you should have a copy from minus pi by 2 to plus pi by 2. That's what you should be having. But the moment you just expanded the n version, you are not only having a copy from minus pi by 2 to plus pi by 2, but the copy whichever is there from pi to 3 pi here, that's sitting now from pi to 3 pi, pi by 2 to 3 pi by 2. Okay, so to get the same effect that you are getting by directly downsampling it, by directly upsampling it from here by a time duration of t by 2, to get the same thing, you should just retain this copy and ignore these, or yeah, these copies you make it to 0. So that means you have now from minus pi by L to plus pi by L, right? So essentially there will be L copies now. In this particular example of this pi, okay, L copies would be there. You just need to pick one copy there. So and then this multiplication factor would come here by L, because the moment you are coming down, you are doing a sampling of the signal, 1 divided by the time period. So this would be 1 by t for your discrete time signal. But if you are doing it by t by L, you should be getting L by t here, right? The earlier expansion you did would still will not touch the magnitude value, remains unaltered, the amplitude along the y-axis. So this downsampling you do by a factor of L and giving you the result there. So multiplication of both would give you the result. That's all. So there is not much here to discuss. All I wanted to emphasize here is look at the similarities between converting a continuous time signal into a discrete time signal that has similarities with downsampling the signal. Similarly, you have like given a discrete time signal, conversion of it to a continuous time signal has similarities with upsampling a discrete time signal. That's the you have similarities as well as differences, because differences is in the discrete time signal where you are downsampling and upsampling, both your input and output are discrete time signals. Whereas the earlier case, in the first case of D2A conversion, you're discrete to a continuous time, and in another case, continuous time to discrete could happen. Discrete to continuous and continuous to discrete. Yeah, those are the two things happening. Okay, so before we move on to the next one, do you have any questions here? Yeah, any questions? before we move on? So if these things are clear, we would then move on to, if you don't have any questions here, we'll then move on to the next, the last part of this sampling. No, by the way, is it clear? At least for the, if you had already gone through the earlier one and then looking into our discussion today, is that clear?
Yes, sir.
Okay, good. No question, no doubts or no questions here? Okay, then let me move on to the second part. Okay, the last part of our discussion for today. Again, let me share the screen. Right. Okay. This is where suppose if you would like to, so far the last discussions, earlier discussions are either to upsample a discrete time signal or downsample a discrete time signal by an integer value. Suppose if I need to do it by a rational function, right? For example, 1.5 times t, okay, that means 3t by 2, so that I could think of it as 3 times t by 2. So you are making the rate at which you are taking samples from t to, you made it to t by 2, so you have double the samples, that's upsampling. And then you are making whatever this is there, this value you are increasing by 3, right? So you are increasing the interval at which you are taking samples, that's equivalent to down sample. So this you could write it as upsample first by a factor of 2, followed by the resulting signal you downsample by 3, right? So for the obvious reason that the moment you are upsampling it, there is no question of if the original signal doesn't have any aliasing effect. The moment you are upsampling it, there is no way you would get, if you are taking more samples, that means, see, if a discrete signal you obtain doesn't have aliasing, means you are already taking enough samples from the continuous time signal. Assume that now you are upsampling it by further by some factor, it would obviously would never result in you are taking even more samples than what is required, right? So there is no question of aliasing. In fact, you are dropping the existing copies, right? After expansion and picking up only that which is required. And then downsampling is something would cause aliasing. So obviously, you first upsample followed by downsampling. Okay, so that's the sequence you do, and then take a look at here. This block diagram is, for example, first you do upsampling. So how do you do? This is the expansion step, followed by you are doing a gain of L and cutoff of phi by L, which we just right now discussed, right? And then while you downsample, if you remember, there were you first to do a low pass filtering to avoid any possible aliasing, correct? Where you could have only, for example, if you are doing by M, pi by M is the cutoff frequency, there should not be any frequency higher than that to avoid any aliasing, okay? And then followed by, you would downsample the signal then by factor M, that module whichever we have it earlier, right? So then you could see there are, this is a concatenation of two low pass filters, and the overall you are multiplying here. So basically in the frequency domain, this is an LTI system. In the frequency domain, you could multiply them together, and hence you would get here a gain of L, right? And cut off, in this case you are cutting off, chopping it off by a value pi by L, here pi by M. So obviously you will take a cutoff frequency which is minimum. That would be, instead of doing it twice, you simply take a cutoff frequency, because here anything less than or equal to pi by L is retained, or anything, in other words, anything greater than pi by L is made 0. Here anything greater than pi by M is made 0. Okay, so obviously whichever is smaller, so that's the cutoff. Equivalently, you could think of it as a low pass filter, a single low pass filter, where you take cutoff frequency as minimum of these two, right? And that's how you could combine these two blocks, and that's essentially what you would be doing here. So then we had a look at an example. The same thing, t prime equal to 1.5 times t. We took a signal which is there from minus pi to pi. Okay, then what would happen to the expander? So 1.53 t by 2 means you need to upsample by 2. We have seen that this gets multiplied, whole thing gets scaled by shrinks by 2 here, so you get it. This whole copy would come in between minus pi by 2 plus pi by 2 itself. Okay, this minus pi to pi would come from minus again divided by 2, so pi by 2 to 3 pi by 2. This is how you are getting the copies. Well, you need to just retain one copy here in between 0 to pi. That would be no, that's if you are doing just this block. Okay, now your L value equal to 2 and M equal to 3, minimum of them would be pi by 3, correct? So you would then apply from minus, yeah, this should be minus pi by 3 to plus pi by 3, right? And then this multiplication should be by a factor L here. So only from minus pi by 3 to plus pi by 3 will be there, then this value will become 0 here. That's exactly what we are drawing here. Okay, just a minute. So that's what you are drawing here. So minus pi by 3 to plus pi by 3, you have this value, and this getting multiplied by L here. So what you are getting here is L by T. Then you are now going to do a downsampling of this signal. So downsampling, so this low pass filtering part is done now. This part is done. So this is what you need to you are remaining with. Okay, so how do you do that? Well, there is a scaling along this omega axis. You are doing by 3. So this whichever is there at pi by 3. Okay, this whole thing gets multiplied by 3. So essentially this would come here. Okay, and then of course the next copy would be coming here. Okay, by 3. No, not even here. Another copy is there, right? And this whole thing, if you let's first look at easy things first. So this gets again in place of L by T, this whole thing should get multiplied by factor 1 by M. That would give you L over MT. Okay, and then how many copies will be placed in between the existing copies now? So basically this copy would go to 6 pi in fact. Okay, this copy would go to 6 pi. So this is not that copy. So how many copies in between now will be kept in addition to this copy, which after we got scaling? In between 0 to, so this essentially, look, this was going to 6 pi. This is going to, this would of course remain at 0 itself. And then the question here is your M value here is M equal to
3, sir.
Yeah, right. So how many copies would be kept in between 0 and 6 pi now? No?
2 more.
Right, 2 more copies will be there. Okay, so that's what you had R equal to 2i plus 1, I varying from 0 to m minus 1. Okay, if you recollect earlier the way we are doing, so 2 more copies are kept. So that is what is contributing to this copy as well as this copy, and of course this this would be somewhere 4 pi, and the other copy, this copy would in fact go to the other place there. Okay, of course you could in fact yeah, Gautam, you had a question?
Sir, can you just explain why we are getting those 2 copies in the between?
Okay. Let me go back to the discrete time processing of continuous time signal. No. Yeah, downsampling of discrete time signal, if you recollect. Just see here the way we worked out here. If you recollect, this was the way we were doing. XD of e power j omega equal to 1 by m into I varying from 0 to m minus 1 x of e power j omega m minus 2 pi by m into I. Okay, if you ignore 0, the first copy, there were again in addition to m minus 1 copies you are keeping. See, think of it in this direction. You are when you are so say downsampling is equivalent to multiplying it with an impulse train that has, for example, here 1 by so more m-1 more impulse values are there for a given length of t, is it not? So that is convolving, that is equivalent to convolution with impulse train. So obviously then you should be having more copies there. Does that make sense? So with the same thing, you could see analogy of the same thing in the continuous discrete time domain also. Okay, that's what in fact we had looked at here. So discrete sampling 3, yeah, no, sampling 5, right? So that's what we exactly worked out here in our 5th module, right? Where this downsampling, so for example, we did it by 2 there, okay, if you recollect. So yeah, I have drawn it here, just remember here. So 1 by m into, if it is 1, you had a copy placed at omega minus 2 pi by 2. So one more additional copy is placed here. So if you had, so you work out here 3, then you would see you would be in fact placing 2 copies there. Is that clear?
Yes.
Right. So I repeat here again, downsampling, if you try to interpret it from the viewpoint of a continuous time signal, okay, and compare it with the already existing discrete time signal. So you have your impulse train, the distance between any 2 impulses was there, for example, t. Now it is t by 2 if you are downsampling by a factor by 2, right? So that would give you more copies of the same frequency spectrum the moment you are downsampling it. So that's why now you try to interpret between these two directly, these 2 discrete time signals, and see that this should be the first one, the second one should be the downsampled version of the given discrete time signal. So if you want to do that, you simply need to keep the additional copies here. If you are downsampling by factor m, equivalent to placing in between m-1 copies. Am I clear? Yeah, Gautam, hope it's clear now.
Yes, sir.
Okay, good. So 1 minute, I could not move from this to the last one. In this, my whole notebook got okay, good. I'm able to move it. See, another way you could simply do is in both the cases, actually, both downsampling and upsampling, there is no doubt you should have the concepts clear. But at the end of the day, simple cross check that you could do, look at is it should be the moment your signal is a discrete time signal, the DTFT of it should be periodic with a periodicity of 2 pi. That's a very simple thing that you should keep in mind. So the moment you are able to get this first copy, okay, this copy, which is there from minus pi to pi, obviously you should be doing that. It's periodic with a periodicity of 2 pi, so you keep it there. So whether you are getting it or not, don't use it for drawing it right away, not trying to interpret the concepts, but rather you use it as a cross check at every point. You could use it while you are downsampling. You could use it while you are doing upsampling. You could do it while you are converting a continuous time signal to discrete time signal. The simple principle that the signal should be periodic with a periodicity of 2 pi. Unless you see, if you are just expanding on the omega axis here, you would see that the another copy is at 6 pi. The copy which is there at 0, you have a copy. Another copy is at 6 pi. So there should be obviously something at 2 pi and 4 pi also. Is it not? So I caution you, use it as a cross check, but not the way to bypass the understanding of placing the copies there. Okay. Yeah. So that's all you do it here. There is nothing more here. We are done with it. With this, changing the sampling rate by a non-integer value, which is a rational function, in fact. Okay, so that's all from my side for this sampling. You have overall, what's your impression about sampling? So maybe I'll stop the recording here. So any other questions, if there are there, then we will keep this recording also, so that might be useful. Yeah, any questions? Any other questions or any other doubts here? And by the way, after this, in my video lecture, I have given a couple of pointers. One is related to the how does this impact when in case of an audio signal. It was like it was in a tool that they were trying to vary the vary or decide what should be the sampling rate and other things. That was a nice demonstration of for illustrating the importance of having a clear understanding of sampling. So in addition to that, I was giving you an example with images where suppose if you are subsampling the images, how you could see artifacts there, and to address those artifacts, what can be done. And after you do that an operation which is somewhat equivalent to low pass filtering, you are doing a Gaussian smoothing, that's after all a low pass filtering, then you could see there artifacts are essentially high frequency content in the image, and you could see there the moment you are low pass filtering it the Gaussian before doing subsampling, you could see in the example I have shown in the video that you could get rid of the effect of artifacts or aliasing, right? And for the audio, that demonstration was, I think, is good enough to get a clear picture of that. Okay, so I'll just stop the recording here, but still if you have then any questions, we could discuss them. Okay, let me maybe keep it in pause.